give. Now, where each of these facets points, that's what's defined as the canting of a heliostat. When the mirror normals follow the normals of a parabola, that is called an on-axis tracking, because they will all focus to the same point at the focal point of the receiver. But it doesn't have to be so, because if you envision a heliostat central receiver system, if you have the receiver and the heliostat, for the light to be parallel to the axis, it would then be blocked by or it would be in the axis of the tower itself. So even if that occurs, it would only occur at one particular time each year, which means that maybe an off-axis canting or a different shape to the overall curvature of the mirror is more ideal. And in fact, what I show you here is a result of a study to find the optimal parabolic off-axis canting system. So what we did is vary the time of year, the time of day, and as a metric we use the annual installation weighted energy delivered to the tower. And we find that we can actually find for this particular configuration an optimal that is, so we cant our mirrors so that at a particular day and time defined by this curve, all the rays are delivered to a point. And that would lead to an overall optimization of the system. And what this looks at in practice is illustrated in this particular point. So here we have a mirror that has lost its canting, or it's not canted correctly, and each of the individual facets leads to a focal point that's all over the place, whereas when the mirror is canted correctly, all the energy then is redirected to a particular point on the receiver. Next, we need to track the motion of the sun. So we have the Euler rotation theorem, which governs rotations of rigid bodies. Basically, it says that, or what we can deduce from this theorem as applied to heliostats, is that we need to move the heliostat about two axes of orthogonal axes in order to be able to achieve any orientation that we wish throughout the day. The sun moves, as we know, one full revolution every 24 hours. That means this many milliradians per second. And for a particular accuracy of about 1 millirad that's typical for central receiver systems, that means that we need to update the position of the heliostats every 10 to 20 seconds. Now, 1 millirad may seem as a very small angle, but if you consider that in large plants, heliostats are placed up to 1 or 2 kilometers away from the receiver, that means that if it was much larger than this angle, then eventually the image would not fall on the receiver itself. So we have to have these very strict tracking requirements, which are much more stringent for heliostats because they rely on the direct component of the radiation, as opposed to tracking photovoltaics, which have a much more forgiving tracking accuracy. There's two main tracking methods that are employed in heliostats. On the left is depicted the azimuth elevation tracking. That means that the heliostat will have a left to right motion and then an up and down motion. I think that's the motion that we're most familiar with and seeing. It's illustrated also here. It's most typically deployed for several reasons, also having to do with actuators that we'll talk about later. But there's also an alternative that is actually employed in the heliostats that you will see at the Bordeaux facility, or the heliostat that you might have noticed as you go towards the lunch. So this is a spinning elevation or tracking, target-aligned tracking system. In this system, the sun, the normal of the mirror surface, and the target, they always lie in the same plane. That means that the mirror will have to have a spinning motion about one of the axes, and then it also has an elevation motion for to control this angle. Now, this is favorable because it reduces the astigmatism. Basically, because you have the sun and the target in the same plane, you eliminate the astigmatism in one of the primary dimensions, which means that you can always keep the image more compact. And that's illustrated if you assume that you have a grid that reflects onto the target. On the left column is the image on the receiver of this grid from a azimuth elevation heliostat or from a rotation elevation heliostat. And you see that throughout the day, for the rotational elevation, the pattern remains more tight, and we can then achieve higher concentration ratios like this. There are also other considerations depending on the tracking method, which has to do with how tightly we can actually pack the heliostats in the field, because land isn't free, so we want to pack these heliostats as tightly as possible within a field. So that's what's defined by the term of collision space, how much free space needs to be around each heliostat to avoid the possibility of a collision, which is drawn with these circles around the square that depicts the heliostat. So what we see is that as a function of the aspect ratio of the heliostat, the rotational elevation heliostats can actually achieve a much tighter packing density. However, for most practical designs where the aspect ratio is around 1, you see that there's really there's not a very large advantage to having one tracking method or another. Now, if your heliostat then has a very large aspect ratio, then you might consider the packing density that can result in the field as a optimization parameter. Next is the actuators that will give this motion to the heliostats. There are several considerations that we need to take into account when picking the particular actuator that we want. The resolution of the movement, we said that we need to have at least a 1 milliradian accuracy on the tracking, so the movement resolution must be below that. The size of the heliostat and the wind loads will define the loads that the actuator needs to withstand. How much electricity these actuators consume, if they have backlash or not, if we can get feedback on their position or not. So all these considerations are what we look in when we select the actuators for the heliostats themselves. Two of the most common actuators are the slew drive. This has a worm gear that will cause a rotation in the inner ring, so that's used both in the azimuth and the elevation tracking of the heliostat. Or we can use a motor moving a screw that would then convert the circular motion of the motor into a linear motion, and that's a linear actuator here. There are many other actuation mechanisms and designs, but there's no need to go into further detail on these. Next, a little bit of the mathematics of the tracking itself. Basically, we know where the individual heliostat is positioned, and we know based on the time of day where the sun is in the sky, and we know where our target is in space. So in principle, we know everything we need about the system to lead to an open loop control system. We don't need to get any feedback from the system itself to be able to determine the position of the heliostat or where the heliostat should point. This is a picture I pulled from a paper showing the algorithm that they used to implement this open axis tracking. Basically, the algorithm takes the time of day, sees the reflected vector and compares it to the ideal reflected vector, and if this vector deviates more than a particular angle, then it will send a feedback to the system to update the position of the heliostat. However, in reality, when we have heliostats in the field, we don't know exactly where they're placed. I mean, you have to have some equipment go and dig the particular foundation that you can survey afterwards, but it's always subject to some accuracy. The ground may shift due to geological processes or other things, or it can settle because of rainfall. So nothing is really where you think it is in reality. And that means that we need to have a technique to monitor the systems and update the feedback that we have. So this is typically done with a beam characterization system that looks at the image of an individual heliostat photographically, determines some metrics, and then updates the software. So here you see a heliostat that it should be pointing there, but it has some offset. So with an image of the individual heliostat, we can generate this calibration or this correction factor that will then have the heliostat point to the correct location at each point in the day.
How you do this without any feedback?
It's not possible to do it without feedback. I mean,
You don't. You make an
you have to make
open loop tracking.
yeah.
So if you have any problem with any step, so it will be offset.
Mhm.
It's good. So how you can that's your
The beam characterization requires feedback. So you have to have feedback, and you have to look at one heliostat at a time to be able to know which heliostat your error is coming from. So typically, this is the image of the receiver. The receiver is on top, and just below it is a secondary target. So one heliostat at a time goes to the secondary target. Here you see it's illuminated by one heliostat, where you get an image like this. And then you process this image, you find the offset, and you'll send it. You say that the particular heliostat needs to have this offset applied to it, so you can track that. Does that answer your question? No.
yeah.
And then you want to do this without feedback. You want to have it in no.
You say you don't have you have an open loop, an algorithm for tracking.
Yes.
Okay, if you start the day and something happen, and one heliostat have error, or maybe
Okay.
many. So how you can check if the error was 3 mainly?
Okay. The problem with heliostat is that typical fields have thousands or tens of thousands of heliostats. So, and they all focus to this area that's the receiver. You see here that the receiver is the square, and outside it you have some illumination. How do you know which heliostat it comes from? So that deconvolving the signal and saying that it comes from the particular heliostat is basically an impossible problem in heliostat fields. So although you do the tracking based on the time of day, that's the only input that you have, because you know where the heliostat is and the target is, you'll need the time of day to be able to point it correctly. But then, on top of that, if you want to improve the accuracy, you need to have a secondary error signal, let's call it, which has to come from feedback. Okay? So, if you would do it only with an open loop system, eventually you would have large errors. You would see this extra energy spilling outside the target being more and more and more. And I don't know, or I don't think the performance would deteriorate over time, but you won't be getting the maximum performance out of your system. So in order to further increase the performance, you need another input that has to come from feedback. Okay? So the final thing that we consider on a heliostat is the structure itself. Obviously, the more metal there is in the structure, the more rigid it's going to be, the more accurately we'll be able to control it, prevent various vibrations or deformations due to gravity. However, the metal costs money, so there's an obvious trade-off between the strength and the rigidity of the structure or the cost of the heliostat. The graphic I showed you earlier is a very traditional heliostat design. There's a pedestal and a torque tube that on the torque tube is the whole structure of the heliostat. However, for small heliostats, there's very innovative, easy to deploy structures that are lightweight. So there's the obvious trade-off again between rigidity and cost. And then people have studied the natural frequencies of various heliostat designs and how they deform throughout time. Now, we also need to take into account the loads that will be applied, and there's some seminal work that was done in the early 80s, I believe, studying the wind loads and wind drag and lift coefficients on heliostats when they're in the field. So taking all these things into account and the particular design of our heliostat, we can find the vibrational frequencies or the natural modes of deformation of the heliostat itself. and then see if we need to further optimize the structure or if this deformation that occurs is acceptable within the overall accuracy and deformation that we have in our system. So far we've talked about the mirrors, the shape that the mirrors need to have, how the mirrors will move, and what the structure needs to be in order to withstand these loads. Next, I told you we'll talk about the performance of the heliostat throughout the year. So the heliostat, the useful energy that we can get from a heliostat field has to do with the direct solar radiation that we have at a particular time, the area of the field, a lump term that's the efficiency of the field, and then we have the secondary term of the efficiency of the receiver itself. That will lead to the decay, or the increase in the decay from the first slides that I showed you of the theoretical efficiency of the heliostat. So the reflectivity, we talked about the reflectivity, solar weighted reflectivity of the mirror itself, depending on the material that we will use on the glass. But there's also the impact of the environmental conditions. So we did a survey of the reflectivity at the heliostats that we have in our field. We have the reflectivity as a function of wavelength for the particular mirror. Now, you can compare this to, it's a silver mirror, so you can look at the silver line and compare it, sorry I didn't put them on the same slide, to what we have. So in fact, we do get very, very high reflectivities for a wide portion of the range. And what we did is we measured the reflectivity of the mirrors at 660 nanometers, that's visible red, so our mirror that we have has a 93% solar average reflectivity, but at the particular wavelength that we use, it has a reflectivity of 97%. So we watched the mirrors and we started doing daily measurements of reflectivity, and we saw that in a 1 week period, we had a decay from about 94% to 77%, so about 15% decay in reflectivity in 1 week. Now, the conditions that we have are extreme, I think, in the particular field that we have that you're going to see on Friday. I don't think the time frame is typical for a particular field, but the decay that you can achieve in reflectivity is typical. So forget about the time scale here, but you can see how the reflectivity will decay, and you can use that information to, when you're modeling a particular field, to do annual simulations. The other thing that's of interest is when the mirrors were washed, how we can recover the clean reflectivity. You'll see that in both cases the mirrors were washed first. There's a slightly different value, but remember, here we achieved about 95% of reflectivity, but remember that the mirrors clean at this wavelength have a 97% reflectivity. So that means that corrosion or other factors have led to an overall decay of reflectivity over the lifespan of the mirrors. And that is something that we're interested in, again, for a 25-year lifespan of heliostats. We need to know how the reflectivity will decay for clean mirrors and on a shorter time scale throughout the duration of the planet. Next, we have the cosine losses. When we have the rays of the sun reflecting off the surface, the actual useful area of the mirror surface is the projected area that the light will see. And that is a term that's proportional to the area and the cosine of the angle formed between the normal and the rays from the sun. And that's why this term is called the cosine loss. So people have come up with maps as a function of where the heliostat is with respect to the receiver. And basically what this shows is that the area directly in the northern hemisphere, the area directly north of the receiver is the most efficient, and as you go to the sides or further back, the cosine loss will become larger and larger because the areas, the angles that you need to reflect over are larger and larger. Similarly, this plot also shows the same thing. They're from two different sources. Next is the shading and blocking losses. As you have the light from the sun coming in, a mirror that's in front may shade the mirror in the back, reducing its effective area, or when the light is reflected, it can be blocked from one heliostat, from the one in front, and the light is blocked. So again, the area of the heliostat is effectively reduced. So this is lump initiating and blocking term. Next is the spillage. Again, I show you a similar picture of all this light that we can see outside the aperture of the receiver. That is a light that is not used, and it's termed spillage loss. So in this, I have I don't know if you can see the blue circle in the center is supposed to illustrate the receiver size, the receiver aperture, and then the contour lines are the flux contours of the parabolic mirror. And you see how this spillage changes throughout the time of day, and probably noon should be your highest. You have a tighter spot and most of the energy falling in the receiver, but this also accounts into some tracking losses. That's why the two are off-centered in noon. Next, we can have, as I mentioned before, we can have heliostats that are as far as 1 or 2 kilometers from the receiver surface. So the air mass that the light needs to travel through can have various particles, aerosols, or other matter that can lead to an attenuation and a further reduction of the light that actually reaches the receiver. This is captured in the attenuation term, and although for small distances it's not very important, this plots the distance in kilometers as a function of attenuation efficiency, and you see how the function decays. At about 3 kilometers, you've lost 25 or some percent of the actual energy due to attenuation from the air mass that's between the mirror and the surface. The same phenomenon is what leads to the decay of the actual radiation that we receive on the surface of the Earth as opposed to the extraterrestrial radiation outside. Okay, there of course there's clouds and other scattering occurring, but it's all within the same losses category. Finally, there's the performance of the tracking mechanism itself. So if we look with the beam characterization system photographically at the center of mass of the heliostat as a function of time, what we get is this particular pattern. So this was an experiment done with the heliostats outside, where you see the control system will cause a motion in the heliostat, and you have this discontinuous motion, and then the actuators freeze, so you have a gradual drift over time of the center of mass of the image, and then once it exceeds these error bars that are set for the control system, it will readjust and go back. And you get this nice peak throughout around noon, where the sun reaches its peak in the sky and goes back the other way. That particular axis doesn't need to track for a long time because the air will always stay within there, and we can capture that with our image processing system. Then there's, aside from the tracking errors, there's other optical errors that can come from the microscopic and macroscopic characteristics of the mirror surface itself. I have some slides that I will show you about the particular example of cases that we have, so we'll talk about these errors a little bit more later. Next is the overall efficiency of the field and how we can combine all these factors to get the best performance of the field throughout the year. So there's 3 different methods that people have come up with. The first is the field growth method. So you have your terrain, you survey every single location that you have available, and you find the most efficient location, and you plant the heliostat there. Now, taking this heliostat into account, you'll do the same process and find the second most efficient location, and put the second heliostat there, and you'll repeat the process on and on and on and on until you get the annual energy that you want in your field. This method gives robust results, but it's very time-consuming. You repeat, it's a brute force method. You keep doing over and over the same calculations. A second way to do it is to follow a particular pattern, where it could be a spiral or a grid or some radially staggered pattern, where you follow a predefined rule on how to space the heliostats, and then you just optimize the parameters of this particular rule. Let's say the spacing or something like that. And then there's finally the free variable method, where you can use more advanced optimization techniques such as genetic algorithms to move all the heliostat locations at the same time as a swarm and find the most optimal configuration. And some results of what you get from this is starting from a particular configuration of a heliostat field that's for the PS10 plant in Spain. From this particular reference, they optimized this configuration. This is I think it's a radial staggered configuration, so you have different rings with heliostats placed along an arc, and then in the row behind you place the heliostats in the gap between the row in front. So they optimized this layout, leading to this design. This is what you get with the biomimetic pattern. It's kind of a spiral pattern, and this is what the free variable method would result in. So you see how you can reduce both the number of heliostats and the land use based on the various optimization technique for the field that you use. Again, with the same objective of the annual installation delivered by the field onto a target throughout a year. Finally, some words about costs and economics. I don't particularly like talking about economics, but it's very important in such systems and renewable energy systems to make them more deployable. Studies have shown that the cost of the heliostat field itself can range between 30 and 50% of the overall cost of the solar plant. That means that even a very small increase in efficiency in this would be significant economic savings. So there's a very large interest in optimizing the cost. So what people typically do is they separate the costs into three categories. The costs that are defined per unit area, so you need glass will cost, I don't know, 30 euros per square meter, independent of if you have 100 or 1 square meter of heliostats. Then you have cost per load, and therefore the area. So you would need a much larger actuator if you have a 200 square meter heliostat than you do if you have a 1 square meter heliostat. And then fixed costs per heliostat. So no matter what, you need to control 2 actuators on a particular heliostat, so it won't change based on size. And then depending on so this plot shows the cost allocation of the category 3 cost from 0.25 to 10%, and how the optimum size of the heliostat will vary depending on that cost. So you can find, and that's basically the reason why heliostats that you find in practice vary so significantly in area, as you saw in the initial slide that I showed you. So finally, the design example that I'm going to talk about is the field that we have here deployed in Proteas that you're going to visit on Friday. The field has 5 rows of heliostats. The heliostats are designed from CSIRO in Australia. Each has 5 square meter of reflected area, and we have 3 focal lengths deployed by stressing the mirror to achieve that radius of curvature that we desired. The first 2 rows have 25 meter focal length, and the next 2 rows 33, and the last row has 45 meters of focal length. Our terrain is slightly inclined, so we've placed these rows spaced appropriately so we can get the efficiency that we desire, and they aim at a receiver that's about 14 meters above the ground level. We also constrain our system to have a 75-degree field angle, so the resulting configuration has 50 heliostats. Now, we talked about the surface error and how that's important in reducing the optical performance of the heliostat. So what we did when we manufactured these heliostats is we had a laser scanner or tracker, which is a device that you physically move over the surface of the mirror, and it will capture all the microscopic variations in the surface itself. And that gives us a pattern such as this, where here what I've plotted is at each particular location on the surface of the mirror, the deviation of the normal vector from the ideal normal vector, assuming that the ideal shape is a parabolic shape. So we see that overall the performance of the mirror is fairly good, aside from the edges where you can get some more significant errors. We can plot error distributions and see what we get. And okay, for our mirrors, most of the mirrors have an optical error of below 1 millirad. So this becomes important in evaluating the total error of the system, because you also have an error due to the finite angle of the sun, and that can help you define the overall error of the system. However, this method relies on the assumption that we know from before the shape of the mirror, which we assume it's a parabola, but we don't really know that. So another technique that we did is to use photogrammetry to find, and laser scanning to find the actual shape of the surface. So this was some work done with the heliostats that you saw outside. We had to paint the heliostats to not have a reflective surface, and you can see here my artistic ability, which is kind of limited. But what we did is take various pictures of the heliostats and then stitch them together in the software. This is a technique called photogrammetry, and we got a particular surface distribution, but also used a different form of laser scanner to also measure the surface. And we compared these two techniques. What we came up with is plots like this. So really the details aren't that important, but what I wanted to point out is that if this was an actual parabola, all these contours should have been concentric ellipses, because that would be what you get from let's say slicing a parabola of revolution. Instead, we get this surface that's non-symmetrical, and that in our particular case is because the mirror was glued onto the structure. So we have this rib-like structure where we use an adhesive to glue the mirror on. In one of the ribs, the mirror has gotten unstuck in the particular heliostat that we measured. That's why we have this non-symmetrical distribution. So knowing the actual shape of the mirror that we have, then we can input this shape into a ray tracing software and see how the heliostat behaves. So this is kind of the results. There's a smoothness parameter that was used in the software, so that's why you have multiple contours. But the idea is to test how how the ray tracing can predict an actual surface of the mirror and compare it to the visual signal that we get. So I took a picture of the intensity. This is at 3 different times of day, and the columns are for 3 different smoothness factors. So we see that overall, throughout the day, the ray tracing software can very accurately capture the distribution of flux that we get. So we can use this information to more accurately model the performance of the individual field throughout the day and throughout the year. From the optical images, we can only see the overall spread of the flux, but we can't really get the intensity information. But if we consider this as a validation technique, then we can say that we can then use the ray tracing tool to determine the optimal flux in the system. So knowing this, we can do the same process for every particular heliostat in the field. So now I'm taking a heliostat in the center of our field and looking how it behaves throughout different hours at the time of, throughout different hours during the day, and for 3 different days throughout the year. For this particular heliostat that's in the center of the field, we don't get a very large variation. We get some seasonal variation in the intensity because of the difference in the DNI, but not that much is going on in this image. If you contrast this to a heliostat at the edge of the field, we see a lot more interesting shapes going on. So again, the size of each square is the same, and the color distribution is the same for concentration that we can achieve from one heliostat. But in this particular case, you can clearly see that the contours would extend outside of the box considered. So then we would have larger spillage losses as we go to the edge of the field. And that's just to illustrate how these parameters interplay amongst themselves and what we have to consider in an overall optimization. So finally, we can put all these things together in ray tracing software. Here I've modeled our particular configuration. I have two different weather files, a clear sky DNI, just assuming perfect conditions, no clouds, and an actual DNI, which so the clear sky is shown with the blue line. The red line is the typical DNI from the typical meteorological year. And putting everything together, we see a diagram of the energy flux that we have. So from a total available power of 74 kilowatts, we have about 15% cosine losses, 9% shading and blocking. Well, shading is here, spillage and absorption from transmission. So overall, our field efficiency, we find a number of 65% throughout the year. So hopefully with this you got a nice idea of what factors affect the performance of heliostat fields and how they all interplay together. If you have any questions, I'm happy to address them.
First of all, thank you for the presentation. I have two questions. First question is, you might have mentioned it. What is the decreased value of reflectivity on heliostats? First question. The second question is, what are the factors that determine the actual maximum size of heliostats?
Okay. So in our particular heliostats, the reflectivity decays because of environmental factors, primarily. So that's the short-term decay that I showed throughout the 1 week period. In 1 week period, we lost about roughly 15 to 20% of reflectivity. So from 95, it went to 75% reflectivity. However, if we wash the heliostats, we can recover the clean value. So what's more interesting is to look at the decay of this clean value as a function of time. And from literature, they've studied this over a 25-year period. Can show you the plots here. So where they're studying for a 25-year period, decay in clean reflectivity, and they find an average slope of about 0.2% per year. Now, there's no real upper limit to the size that you can become. It just becomes a trade-off amongst your cost parameters. So I think it would be mostly economic considerations that would govern the maximum size of the heliostat. I mean, you can envision a single heliostat that has 10,000 square meters, and that's all your one heliostat for a particular field. But it's not very practical to build a structure so large, have it move with standalone loads, so that's why the technology is kind of fragmented into smaller things. If you consider that the other end of this spectrum, then you have the solar dish. That's a really large heliostat. It's the other point focusing technology. So it's a really large mirror that focuses to a point. Dishes, I think they go up to, most are in the 20 to 30 square meter range. There's the very large dish in Australia that has a 400 or 500 square meter area, but this is a really monstrous structure. So again, I think overall it's economic considerations that would define the maximum size of the heliostat. Any other questions? Yeah.
The two kinds of heliostats tracking, let's say, one is azimuth elevation, which is the most, let's say, common used, and also the other one, which is elevation spinning axis. Basically, the tracking strategy has an impact on the parabolic shape of the heliostats.
Not on the shape of the heliostats, because the parabolic shape itself will give the maximum concentration, assuming you're on axis. But it will give it will kind of help that shape perform the best. So because you maintain it's kind of hard to explain. It's basically you're reducing the astigmatism of the system, because one axis is always pointing in the same direction. So that axis doesn't have astigmatism, So your overall, the distribution of energy is more tightly packed. So that's the advantage of this tracking methodology.
I'm more referring, for instance, the heliostats of Pentagon, they are using this spin
Yeah.
tracking strategy. Would you have exactly the same shape using azimuth elevation tracking strategy?
So if the shape of the mirror would be the same,
Yes.
yes, the shape of the mirror would be the same.
Okay.
But
It's not more parabolic, for instance.
no,
Okay.
but probably that the spillage losses throughout the year would be different. So the shape, the axis of curvature and the focal length will depend on where the heliostat is placed.
I guess also when we go to very small heliostats, we can use totally flat facets, so it plays also into the trade-off of
In the economics, yeah.
system.
Any other questions? Thank you very much.